Okay, so just briefly, I wanted to give a little introduction. I didn't know Phil gave these great introductions to us, but a little background about myself. So I have only recently moved to the UK. Before this, I was a assistant professor at Carnegie Mellon, and I still sort of am. And I did my PhD in linguistics, actually, before that. And now, since last year, I've been at DeepMind. And I work on a lot of stuff trying to marry sort of linguistic theory and computer science. So if any of that sounds interesting to you, I'm the one you want to talk to. Okay, so the practicals this term are going to be basically, we're going to start off next week while we're away. So I assume Phil told you last time that we aren't meeting on Tuesday and Thursday, but you will have your first week of practicals. So there's going to be an introductory practical that's going to just get you familiar with some of the stuff that Ed talked about in the first lecture. It's going to be more qualitative. You're not going to have to implement anything. It's going to be a little bit of exploratory work. Then when we return from our conference, we are going to hand out a big multi-part practical that you're basically going to do over the course of the remainder of the term. And it's going to be a little bit choose your own adventure in the sense that you're going to be able to, it's sort of like a a la carte menu or something. You'll have a list of projects you can choose from based on your interests. We're going to, be clear on, you have to do a certain amount of these things, but basically, depending on what you like, you can pick. And you can also work to a certain extent at your own pace throughout the course. There will just be one report submitted at the end of term. Now, I will say each student is responsible for their own work. You are adults, and you should talk to each other about things. But we do want you to. This is really the opportunity to learn a lot of really good stuff. So we want you to do this yourselves. Okay, so I'm going to now go over the topics that are going to be covered that actually I'd say are important for deep learning and NLP as it stands at the beginning of 2017. And we're going to be covering a lot of these, or optionally you can choose to dive deep into a lot of these in the course of your practical. So the very first sort of most basic thing that you've got to worry about in deep learning and NLP is perceiving and representing text. So Ed just gave a whole lecture on how you might represent text. But we didn't actually we sort of assumed that we knew how the text was perceived by the computer to begin with, namely that we have this list of words that we can map a text to a sequence of word tokens. This turns out to actually be a fairly non-trivial problem. So you have to make decisions when you're working with text data about how you're going to deal with unknown words that you've never seen when you trained your model, when you want to go apply it to some new data. We're always creating new words. This comes up all the time. You also get new words because people spell things differently. People will also maybe put them next to some punctuation. So if you just split, say, on white space, perhaps you're working in a language like Chinese that doesn't even have white space in the language. So all of these things actually turn out to be really difficult. And the sort of standard idea in deep learning is that we want to start with kind of uncontroversial representations of the input. We want to work with these sort of basic percepts, and then let the model learn how to put them together in sort of meaningful task-specific ways. So there are a bunch of things you can make decisions about how you might want to pre-process. You'll have an opportunity to explore some of this stuff. So there are generally going to be some trade-offs. So sort of the more aggressively you split things up, maybe you go all the way down to just individual sequences of characters or bytes and represent text that way. Obviously, you're going to have fewer out-of-vocabulary words at test time, but you're going to need much more complicated models. Your model is going to have to figure out that there's something word-like that exists in your text. With larger perceptual units, maybe you can get away with simpler models. I mean, word2vec works pretty well if you have things that look like words going into it. But OOVs are going to be a bigger problem. So another thing is this depends a lot on the kind of data you're working with. So if you're working with something that looks like this, these guys have editors who check that they've spelled things just correctly. They use the right kind of consistent punctuation, things like this. On the other hand, if you're working with data like this, which you might want to, there's actually I picked these tweets because they have both weird sort of dialectal variants in them, and they potentially have useful information in them. So if you're going to be working with this, you probably want to be somewhat careful. So one way of looking at this is to look at as the size of your corpus grows in tokens, how many unique vocabulary items are you likely to see? And this curve is called Heap's law. It's sort of the bane of the text modeler's existence. It means that no matter how big your corpus gets, you're always still going to be seeing new words constantly coming into your corpus. So you've always got to have a strategy for dealing with these things. And basically, the top line here with this really rapid growth, that's Twitter. And the really slow growing line, that's the Wall Street Journal. So, basically you have very different strategies you can work with to solve these problems. So again, things to keep in mind. So once we've engineered some precepts, some percepts, this is an engineering problem, then we can turn to representation learning, which you just learned a lot about. And in practical one, we're going to use just the standard, simple idea of predicting the contexts that the words tend to occur in. We'll suggest that you use the word2vec tool. So basically, it's just going to be up to you to decide what vocabulary you're going to operate on. We're going to give you a couple of corpora so you can compare what the word embeddings you get out of these different corpora look like. So it's more of a kind of qualitative analysis. Okay. So moving on, though. So this is just sort of a warm-up practical. We can now talk about some other topics that are just big and deep learning for NLP, and we're going to also have an opportunity to explore. So the first, text categorization, which we affectionately abbreviate as TextCat, is the problem of taking a text document or sentence as input and making some prediction about it. So that might be give email, let me predict if it's spam or not spam, or urgent or not urgent. Things like that are text, this is text categorization. A much sort of bigger set of topics you might loosely group under the heading of natural language generation. And the first one of these is a sort of, I think, the most classic problem in natural language processing. It's called language modeling. We basically want to build a statistical model that generates random strings of text, similar to the distribution that model was trained on. And you can also look at this as assigning probabilities of sentences in a language to all strings. And so these are cool. Language models are a problem that have been solved incredibly well by deep learning methods. They also have really good applications. So anytime you do typing on your phone and you don't quite hit the right key and it autocorrects for you, well, it's autocorrecting based on its language model. And so if you have a good language model, you'll have fewer embarrassing autocorrection moments. Or you could try and build a language model to make more embarrassing ones if you wanted to. A more interesting application is conditional language modeling. So this is when you condition on a little bit of side information and generate an appropriate textual response for that context. So this might be something like, say, you work for a company that has a lot of information about the demographics of its users, say Facebook, for example. And you want to know, you don't want to just have autocorrection in general, you want to have customized autocorrection based on, well, this person is a tween, they're probably going to be talking about, I don't know, whatever tweens talk about, or old people like me, I'll talk about, autocorrect my spelling of language model up there. So you can condition on things like that, but you can also condition on much more interesting data sources. So you could condition on a representation of a picture and say your language modeling task is to predict sentences that describe the picture. Or you could condition on a representation of speech, and your model would describe the distribution over transcriptions of that sentence. So these become really, really very important tasks for us. So the second big heading that we might think about our practical tasks as falling under is natural language understanding. So the first sort of set of these things is actually another kind of conditional language modeling application. So we're basically putting these two parts together. So basically we want to condition on text and natural language understanding and then do something. So we want to kind of understand the text. And so some text in, text out applications are things like machine translations. So if you want to know how Google Translate works, stick around. We'll cover that in a few weeks. Another application that we can use very similar models to solve is text summarization. So if you don't want to read that whole article, maybe you could get a quick 2-sentence summary out of it. So summarization can be done quite well with deep learning. Conversational agents are another kind of thing. Maybe you just want somebody to talk to because you're afraid of humans. None of you, right? That could be something where we also we're listening, the agent is listening to the things you say and the things that's said in the past and trying to come up with a good response. So natural language understanding is a huge area, though. It also includes things like if you want to build an agent that goes out and follows instructions to operate in the real world. Question answering is another really important one. So if you want to be able to ask questions rather than trying to do a Google search for yourself, maybe you just want to type in a question specifically and have it come back. And dialogue systems. So we talked about conversational agents, but maybe you want to build a sort of more useful dialogue interface, so a natural language interface. So these, I would say, all fall under the rubric of natural language understanding. And finally, I'd say there are some analytical applications. So these are things that help you understand a collection of text. So if you've got a big corpus, say 100 years of articles published by the BBC, we'd like to maybe understand what topics were important at different points in time. We don't have time to read 100 years, but maybe a computer does. So that's the kind of stuff you might want to do with topic modeling. And then there's also linguistic analysis. So when I occasionally think back to my old days as a linguist, we often want to automate the kinds of analyses that linguists do, and we can do that very well with deep learning techniques. So we can uncover insights about how language is working. So these are all, this sort of circumscribes, I'd say, kind of everything that people are doing with deep learning right now, and we're going to be able to touch on not all of these, but a lot of them. Yeah?
Can I ask, what's the difference between dialogue systems and conversational agents?
With conversational agents, I'm more meant just somebody to kind of talk to, like that doesn't actually go out and do something. And with dialogue systems, we usually mean, I want to, I wasn't being very precise with that. There's some overlap. But what I had intended when I wrote this as two separate things was dialogue systems are things that help you say book of light, and conversational agents are just talk, chit chat. Okay, so the way we're going to do this, obviously this is a huge area. We want you to cover, be able to look at as much of this as possible. We also, however, don't want to spend our time putting together 100 different data sets, one for each of these things on the list. And so the way we're trying to sort of make both sides happy is we are going to work with a single data set that actually has lets us work with a bunch of these different subproblems. Now, some of your favorite things might not be on there, you can do that in your next course. But I think we've got a lot of things to choose from. The other interesting thing about this is it really reminds you, so this is something that you don't often get in courses, and I know this because I've been teaching classes like this for 5 or 6 years, and this is the first time we've sort of picked a single data set and we're saying we're going to use it for a whole bunch of different things. But in the real world, and actually even in the real academic world, where you don't have to sort of even leave the university for this, but once you get outside of courses, we're presented, the universe is giving us data, and it's half of ML is coming up with really interesting ways to think about the data and figure out what you could do with it. And so you're going to be doing that a little bit in this course. So our data set is going to be the corpus of TED Talks. And so this is great for a bunch of reasons. So, there are a bunch of talks on sort of a whole bunch of different topics, but they all have roughly the same structure. So a TED Talk, it doesn't take very long to figure out, hey, I'm reading a transcript of a TED Talk. It doesn't matter what it's about, you can tell. So there's sort of this stylistic uniformity. It's also, there's enough data there that we can learn some interesting things with the kinds of models we're going to be working with this in this course, but they're small. The corpus is small enough, if you take all the TED Talks together, it's small enough that you can work on reasonably limited computational resources. There's also a lot of interesting data associated with each talk. So we have things like topic labels that the TED fans went through and they curated this set. We've got titles. There are summaries that people have written. We have topic labels again. There's, of course, video. We have alignments to the video. We even have translations into that's supposed to say 100 languages. And then finally, we have this, ultimate point, which is who doesn't want to listen to a computer-generated TED Talk? I mean, this is the kind of thing that if it's good, gets you on Hacker News or something. This is what our data looks like. So it's not, it doesn't look like sort of Kaggle competition data. But on the other hand, you're not going to be scraping a website to get this. So, it's kind of close to the real world, but not like you're going to be spending your time wasting it on data cleaning. So basically, just quick look at the talk. So we've got about 2,000 talks. Each talk has multiple topic labels associated with it. Multi-label classification is actually a really interesting problem that I think could be very well solved with deep learning. That there have been a few kind of preliminary attempts to solve it, but not so much. There's a title, so you could imagine predicting the title given a talk content. There's a brief content summary. There are alignments with frames in the video. There are about 5 million words in total, so this is sort of really good size. There are annotations for where the audience applauds and where they laugh. So you can do things like a predict, if I say this sentence, are people going to laugh? Haha. And there are these translations. So volunteers have gone through and translated these talks into actually over 100 languages, although only a few languages have translations of all the talks. So sort of some statistics, you can look through the slides later. Basically mapping these tasks onto what we're actually going to be suggesting in the practicals. So at the beginning, we're going to be building word embeddings from our TED Talks. We're going to be predicting these topic labels for our sort of text categorization part of the assignment. We're going to suggest strongly that you start with that one because that'll be sort of an easy way to get going before we've taught you really anything about deep learning. With natural language generation, we can use language modeling to do things like generate random TED Talks. We can use conditional language modeling to generate TED Talks about a particular topic. So each of these TED Talks has, between 1 and 29 labels. So you can pick, I want a TED Talk about design and sports and global warming. And you can, have it put those three things together. And from the natural language understanding section, we can build a TED Talk translator. And so we'll read in a TED Talk, say in English, and try and predict what its German translation looks like. Or we can read in the content of the TED Talk and try and build a summary of the TED Talk. And then, unfortunately, we don't have any annotated question and answer pairs, so we're going to have to skip the next couple of things. But we do have some interesting opportunities for linguistic analysis, so we can do things like try and predict, that's supposed to say speaking time for sentences. So we have these alignments to video frames, so we could know when people spend a lot of time saying things, and we can try and model that. So can we say, where are people going to slow down when they're giving a talk, or where are they speeding up? We can also think about laughter as a kind of linguistic annotation. It's a linguistic annotation that the audience is providing, but there's this long stream of text punctuated by periods of laughter. So we can try and predict things like that. These are going to be, you'll see these, you'll probably see a few more things, but you can see just from this one sort of somewhat small data set, there's a lot available. So before I end here, well, first, are there any questions sort of about the practicals? I haven't done practicals at Oxford, so I don't know if this is completely off or weird.
Well, short question, where can we get the data set? Can we get it already?
You can actually get it. We'll be posting we'll be providing a GitHub link where it's already downloaded and everything, so you can clone that. When you go next week to the practical, we'll certainly have it, but I think we'll be able to email out the little script that you're supposed to follow anyway, and I'll have all the information. Yep. Okay. So a quick word about software and practicals. So deep learning is, people have a couple of definitions, and everybody tends to say, well, it's obvious what deep learning is, but then if you ask two people what it is, then they tend to disagree. So I try and avoid that. I characterize it more as a way of working, where basically we used to spend, in more shallow learning methods, we spent a lot of time worrying about features and how to map problems onto existing models. With deep learning, we spend a lot more time trying to engineer models and doing less and less with feature engineering. And so the workflow that we work on is we design models, we implement them, test them, analyze the results, and then repeat that process. And so we basically want to iterate on this as quickly as possible. And that implementation step is non-trivial. So deep learning works by optimizing functions. And these functions are big, complex things. Now, they're built of modular, reusable pieces. This is what lets us sort of characterize, develop an intuition for how they're going to behave and for how we should solve problems. But still, if you were to code these things up from scratch, it's quite a difficult thing. And especially the derivative calculations are easy to get wrong. If you make a change in the sort of forward pass of the model, there's a corresponding change in the backward pass. And if you're not careful to keep those in sync, it can go badly wrong. So the solution to this engineering problem is that people use toolkits. And we are right now sort of experiencing a sort of flowering of all possible different toolkits. There's not a clear winner right now. And these toolkits provide standard sort of neural network component building blocks, linear algebra primitives, nonlinearities, operations like convolutions. And then crucially, they provide facilities for automatic differentiation, which means you don't have to work derivatives out by hand now that you have finished your intro ML course. The toolkit will do this for you. In this course, you're going to be free to use your own toolkit, whichever one you prefer. However, the demonstrators, Giannis and Ishu and who else? Brendan, yes, those three demonstrators. They know Torch and are interested in the newly released, as in yesterday released, PyTorch. And TensorFlow. Ishu especially knows TensorFlow. There are many other options, though. Theano is quite popular. I wrote one called Dynet, so I won't be heartbroken if you choose that one. It was designed for language, so it's not the worst choice for this course. You can also, since I wrote these things, I actually think about them a little bit. So you can, I'd say, split toolkits in sort of two dimensions, one high-level dimension, which is how do you declare the computation that you're going to be executing for each prediction or training run. So the first style I call static declaration, which is exemplified by TensorFlow and Theano. You write down a symbolic expression that represents all the calculations you're going to carry out for the training instances and test instances in your data set. And that calculation is basically going to be static. So if you have some variability across training instances, your graph needs to encapsulate the ability to deal with all of this, this variability. And then once you write down this symbolic graph, or you write a program that generates this symbolic graph representation of a program, then the toolkit optimizes it, and it gives you basically code that lets you train and make predictions. So the great thing is you have this graph, you can run all the best compiler optimization techniques on it and get really fast code. On the other hand, a newer or alternative technique is what we're calling dynamic declaration. And in this case, you write code that just computes the predictions you want. So you think, well, I want to first take this vector and then multiply it by this matrix, and take a tan h of every element and follow that by something else. So you write down that code imperatively and execute it. And what the toolkit does here is while that code is running, it's keeping track of all those operations and building up a symbolic representation behind the scenes. And this is based on things like operator overloading. So it tends to exist only in fairly high-level languages. The pros and cons. So the static approach, you can optimize the computation graph. So in the way that sort of compiled languages are faster than dynamic languages generally, you can expect similar performance improvements. The problem with this, though, is you have to basically write a program that writes another program. And that second program that gets written might not have all of the facilities you want. It tends to be a sort of high-level declarative language. On the other side, in dynamic execution, you write code in your favorite language, as long as your favorite language is Python or C, C++, and then it will do the work for you. So all of the time you spent learning to program in Python or C++, you can then leverage you don't have to learn a second language, basically, that gets written. The learning curve is lower. The downside is the toolkit has fewer opportunities to optimize, so you might expect that it's slower, at least in the limit. Because one of the interesting things that we just recently discovered was that basically across, going from left to right, we move from dynamic to static, where higher is better. This is performance, how quickly we train things. And we actually see that in general, we're doing about as well with dynamic toolkits as we are with static toolkits. So Chainer is another popular dynamic toolkit. It's absolutely beautiful Python. It's a little bit slower. And on the y-axis, these are just different tasks. Anyway, this is just something I wanted to leave you with. I don't often get to talk about my engineering work, and so I thought I'd get a captive audience here. And it's sort of at the beginning of a course on where you're going to have a big practical component worth mentioning. So enjoy the practicals. This term will be evolving them. Please give us feedback as if anything comes up. So thanks.